Welcome to part 2. In this part of the electrostatics review, we're going to look at part C, finding the field at this random position P. And then also we're going to look at another question that relates to just F equals QE, forces on things that are in an electric field. Okay, so I'm going to use this same diagram here for part C of this question here. Only now I'm not going to ask for the force on any particular... Clearly I'm doing this at school. I'm not going to look on for the force on any particular charge. I'm going to look at the electric field at position P. So I guess a couple of things we got to say about electric fields. Number one, electric fields exist whether or not there's anything there for them to act on. So I can calculate the electric field at P without necessarily implying that there's anything there. It may just be an empty point in space, right? There's no charges there that it could even potentially interact with, okay? But if there's an electric field there and then a charge appears there or moves to that position, then it would experience a force. And the force that it would experience would be proportional to its charge, right? The meaning of this unit for electric field is it tells you the number of newtons that act on a charge per coulomb of charge on that charge. Okay, so if I were to calculate the field here and we get that it's like 5 million newtons per coulomb, that would mean that if I then put a 1 coulomb charge there, it would experience 5 million newtons of force. That's never reasonable. Right? You don't ever find a 1 coulomb charge in one place. I mean, usually. But if we put something more reasonable there, like a microcoulomb, it would experience 5 newtons of force, because 5 million times 1 micro is 1 times 10 to the negative 6th. Okay, so 5 million times 1 millionth is going to give you just 5. Okay. All right, let's actually then set about our work of finding the electric field at P. Oh, I guess the other thing I meant to mention, always something else. Fields always go, maybe I already said this. If not, then I needed to say it. Fields always go away from positive charges and towards negative charges, right? So if I calculate if I draw in some vector arrows, which would be my first part of finding the electric field, the field that this one produces at this point would go away from it. The field that this one produces at that point would also go away from it, because those are both positive. The negative one would go towards it. So there's that one. All right, if this one were a positive charge as well, then that field would have gone in the exact other direction. All right, now let's actually calculate it. Like with forces, I had to have the vector arrows on there so that I could calculate components for things, and we start with the exact same procedure. Right? We're going to say the field due to, let's say, the minus here, is going to be KQ over R squared, R hat. All right. R hat for this one is just going to be I, positive I, because that field is directly to the right, 100% in the positive I direction. So really all I need to do then is plug in what R is. Well, based on the diagram that I drew, if that's D and that's D, then this is 2D altogether. So 2D squared. That's going to give us KQ over 4D squared I hat. Okay, so that one's done. All right, if I look at the fields from the two positive charges, the first thing that should leap out at me is one is up-ish and one is down-ish, which means that if those two are equal charges and these distances are the same, which according to the diagram they are, then that means that the j components of those two should cancel. So that means that if I take the field from the two positives, fields from the two positives, and I add them together, I will have no j component, only an I component. All right, and that's going to look like this. 2 kq over 2d squared. All right, and then I've got to do something with the r hat. Let's back up in case you're confused. Like, what? The 2. I have a 2 there because there are 2 charges here, therefore 2 electric fields. And the component I'm keeping from each one is the I component. As we discussed, the j component's going to cancel out, so I'm keeping the I component from each one. Since I've got 2 of those and they're identical, I'm going to multiply whatever answer I get for one of those components by 2. All right, next. The r hat is going to be, first of all, in the negative direction for the I component. Second of all, it's going to be based on the angle from the horizontal, if I'm going to say that it's cosine. Okay, so there we are. I picked that angle. According to this reference triangle, cosine theta, which is adjacent over hypotenuse, is going to be d over 2d, which is 1/2. All right, so that means that the I component is negative 1/2 I from each of those. All right, if I multiply this all out, this will be 4d squared. This 2 will cancel that 1/2, and we get negative kq over 4d squared I hat. All right, so what does that mean? The total the electric field's going to be 0. It's amazing. Those will exactly cancel out. I actually did that on accident. That's a pretty remarkable result. Okay, but fine. It's going to be 0 there because it's going to be 0 there. All right. If I picked almost any other point, that would not have happened like that. So if I picked, say, over here a little bit, then those components would not have been the same. If I picked the exact center here, the origin, right, the components from the 2 positives would have canceled out, but you'd still have had an electric field from the negative. So it would have been something in the positive, kq over d squared in the positive I direction. Okay, so that's that one. If it doesn't work out as pretty as this when you're finding an electric field, I mean, don't be concerned. Most of the time, they don't work out that nicely, right? If I said find that electric field like at this random point up here, that would have been a lot more complicated and you would have got an uglier result. So if some of the ones in the homework end up with like an I component and a j component, that's perfectly normal and that can definitely happen. All right, let's look at one more. This one is going to relate to just the equation F equals QE, and also some basic review of forces, because there's going to be some problems that you'll see in the homework that I assigned where you have to use like components of forces all over again like we did first semester, okay? All right, so the question that we're being asked here is to find the electric field in terms of gravity and the angle theta. So I think probably what you'd need here would be something like there's a charged object, like a piece of styrofoam or something, on the end of a string, and there's like a wall over here that's charged, and so it's producing a uniform electric field that way, and due to the uniform electric field, this thing swings outwards. Okay, so it's electrostatic repulsion, right? It's pushing it out this way. Alternatively, we could say there's a oppositely charged wall over here, and it's attracting it this way. I don't know. It could go either way. It doesn't especially matter which one we choose to do. Okay. if we want to work out what that electric field is in terms of like this stuff here, we've got to draw in the forces. Okay? We've got gravity. You know what? Let me just use black. Gravity is straight down. The electric force, the force produced by an electric field is always either parallel or anti-parallel to the electric field. And which one it is depends on whether it's a positive or a negative charge. The way this question is written, the field goes this way. That means that if this is deflected that way, this must be a positive charge, even if I hadn't told you as much. Okay? So it's been pushed this way by the electric force. Let's call it F. Or sorry, how about QE? Because that's the equation I'll actually use for the electric force. All right. The force would have been in the opposite direction if this had been, say, a negative charge, and that's all that would have been different. It would have just swung out the other way. All right, and then the third force that must be acting on it is going to be the tension. Right? Absent the string, it would fall and be pushed that way by the electric field. So, tension. All right, so sum of forces. Let's say in the x direction, we're going to have QE minus T sine theta. All right, if you're not sure why it's sine theta, then you should pause the video a moment and think about how trigonometry works and which side of the tension vector is going to be in the x direction, and therefore which trig function would give it to you. And the forces in the y direction are going to be mg minus t cosine theta. All right, t can't really be in the answer because it's not a thing that we know, but we do know the mass and we do know the charge. Both of those are given to us. So we need to do a little bit of algebra to like make the tension disappear. That's not a hard thing. We can just take this equation and solve for the tension. Right, move this over, divide by cosine, and we'll get this. And now we can sub that in to the other equation up there. So QE equals T sine theta. T equals this right here. All right, so that means that the electric field is mg over q tan theta. All right, now we happen to know what m and q are, so I could plug numbers in for those. If we also had a value for theta, then we could plug in a value for theta and we could work out what the electric field is. But as you can see, the larger the electric field is going to be, the greater the angle is going to be. I mean, that's how tangent works, right? A bigger angle corresponds to a larger value for tan theta. Let's ask a little extension question here. How big would the electric field have to be in order for this to swing out completely horizontally? Totally horizontal. You can pause the video if you're tired of watching me think. Actually, I'm done thinking about it. So, but if you want to pause the video and think yourself, go for it. The answer is never. You can't actually have a large enough electric field in order for that thing to go out horizontally. Plug in tangent of 90 degrees, and you know, or you should know what you get. It's infinity, right? That's it's not a value that your calculator can tell you, because it's infinite, okay? So there is actually no electric field that could be large enough to make it go out horizontally. It'd have to be technically infinite, okay? All right, which means not happening. All right, check out part 3, which is about electric potential.